Before we jump into the data, here is our presentation plan for next 15 minutes. We are going to track down the invisible threat that's eating our hearth from the inside out. Specifically, we will look at how water travels through the furnace, the flash point, where it starts destroying the bricks, and the 200 micromillimeter gap that kills our heat transfer. By the time we finish, you will have exact data on why we lose 20% of our brick thickness to this damping condition caused by the water increase, and a clear roadmap for breaking the cycle of the hearth failure. Coming to the invisible threat in the hearth. Have you ever looked at the Hearth campaign that should have lasted 20 years but barely made 10? And well, actually, have you wondered what we missed? On the left, we have got that classic orange glow of a healthy iron tap. But on the right, look at that grey, crumbling carbon brick. It's riddled with the deep cracks and looks like a dried out riverbed. Think of it like a secret pest, like termites eating the wood inside your house. Everything looks fine on the outside, but the glue inside is being destroyed by the water vapor. If we don't identify this hidden guest, we are not just losing brick, we are losing the actual foundation of the furnace. So, how exactly does this pest get into our high pressure system? This is the slide which brief on the six intruders. Here the things about our hearth. It's the lowest point in the building. And look, gravity always wins. We are looking at a furnace cross section with six glowing blue arrows all pointing down toward hearth. It shows leaky pipes, wet grout, and even damp air all heading to the same spot. Think of the hearth like the basement of an old house. If there is a leak on the roof, the water always end up in the basement eventually. The highest tech consequences which leads every drop of moisture, no matter where it starts, is being pulled straight to your most expensive asset at the bottom. But why is our solid brick so sensitive to a little bit of steam? This is a question which is going to be explored in a subsequent slide. Coming to the recipe of a carbon brick. If we call it a carbon brick, why is it actually full of rock and sand? Here, an exploded view of a brick. Most of it, 84%, is that dark grey carbon matrix. But see those colorful floating triangles. Those are the ceramics, silica and alumina. Think of the carbon as the glue that holds all ceramic bricks together. Water specifically eat the glue. Once the glue is gone, the ceramic are just floating there, useless. To prove this, I wanted to set a trap in the lab to watch it happen in real time. So, setting the trap is our next slide. We wanted to be 100% sure, so we built a teeny furnace inside a jar. This is a diagram of our test. We have got a small carbon brick cylinder with a glowing red core of hot iron, all tucked inside a strong container. It's a science experiment in a box. We wanted to see exactly what happens right where the hot iron meets the brick. By controlling the air inside, we can finally tell if it's the iron or the damp air that's doing the damage. We ran this test under three very different weather conditions, and those three weather conditions or three atmospheres are as follows in this slide. Is a little humidity really that different from a full blown pipe leak? You see three jars here. On the left is dry jar, in the middle 50-50 mix, on the right a glowing jar of 100% water vapor. We are basically comparing a dry desert to a rainforest to a monsoon, all at 1500 degrees centigrade. So temperature remains constant. These allow us to measure exactly how much more damage happens for every 1% of moisture we let into the hearth. And the result shows there is a very specific flash point where the brick start to fail. And briefing the triple point on this presentation is in this slide. So at what heat does the invisible thread become a guaranteed attack? So look at where those lines cross. That is 650 degrees centigrade. Below that white dash line, the reaction must happen. 650 degrees centigrade is the flash point. Once it gets that hot, the water is chemically guaranteed to attack the carbon. Since our hearth is very hotter than 650, if water is present, the destruction of your brick is not just a guess, it's a fact. So, what does that fact look like when we pull the samples out? So, here is the slide which shares the naked eye test. As you can see, the difference between dry and wet is, well, it's amazing. Look at the three sample. The dry one on the left is a perfect circle, but the 100% water on the right is jagged, eaten away, and look like mouth-eaten sweeter. In dry air, the brick and iron are best friends. In wet air, they are at war. We are seeing a massive material loss before the iron even start to move. The air alone is turning the brick into gas, and when we put a ruler to it, the numbers are even dangerous. So the shrinkage hook is going to see in this particular slide. So how much of your brick can simply vanish into thin air? Look at this bar chart. The dry bar is at zero loss, but the 100% water bar shot up to the top. Nearly 20% of the brick thickness disappear just before being in damp air. You are not just losing a few millimeter, you are losing a fifth of your protection before the job even gets going. But the real danger is not just the missing carbon, it's the gap left behind. And about that, we are going to discuss in this slide. So, in a perfect world, the iron and the brick should be welded together. This is a very close up picture. See how the white molten iron on the left is perfectly joined to the grey. Carbon brick on the right, no gaps. So it's like a perfectly glued joint. It flows through it easily. This perfect touch is the only way your cooling system can save the floor. If they are not touching, the cooling cannot reach the heat. Now look at what happens when the invisible wedge moves in, which is shown in the next slide. The invisible wedge. Here it is, the real reason Hearth failed. Look at that. That's a 200 micromillimeter wedge between the iron and the brick. We call it the invisible wedge. It's a literal wall of air that acts like a blanket, blocking the heat. So, what is the result? Zero heat transfer. The cooling system on the outside think everything is fine, but the floor is actually overheating because it has been unplugged. So, why did that gap form? Because the glue we talked about is gone. So, that is the main reason. Coming to the leftovers. So when the carbon is gone, what's the left behind the protect uh, to the hearth? Nothing but dust. On the right, that green map shows where the carbon used to be. It's just a black void now. On the left, those yellow dots are the leftovers, the ceramic bits. The water vapor turned the carbon into gas, leaving behind a powdery, useless pile of rock. You can have the best additive in the world, but if the carbon glue is vaporized, they have nothing to hold on. So, how does this process actually play out step by step? So, this mechanism phase, which is supposed to be most important outcome of this presentation, is going to be discussed in the subsequent slide. It all starts with a single leak and a lot of gravity, as we have discussed already in the beginning of the presentation. So look at the blue drops. They are leaking from a pipe high up and running down the wall, following the cracks. It's a silent invasion. The water doesn't stay where the leak is. It uh, comes down to the bottom. The, it follows the gravity rules that we have already discussed. Gravity pulls distant leak directly to most vulnerable spot at the floor. Once the water reaches the hot zone, the chemistry takes over and the mechanism of phase 2, which is in this slide, is showing. This is where your solid armor turns into brittle sponge. See those little green Pac-Man icons? Those are water molecules eating the carbon. The brick is literally turning into gas. The brick is being hollowed out from the inside. The structural loss happens to your solid, which are protecting bricks, is now become soft, weak sponge that can no longer hold back the pressure of the iron. And once it's a sponge, the liquid iron finishes the job by penetrating through it. So, coming to the mechanism number 3, which is also very important. So, here is the final blow. The scab, that weak spongy layer, finally break off and is swept away by the flowing iron. It's like a scab peeling off a wound too early. Once that layer peels, fresh carbon is now fully exposed for the next attack. The cycle doesn't stop, it just resets. This brings us to the most important diagram of the day, the fatal cycle. And which is summarizing the all mechanism that we have discussed so far. So, in order to protect our precious hearth, we need to avoid the water ingress at any cost, and that is the only one and the last solution for campaign life extension of blast furnace hearth.